Okay, everyone, welcome back to section 7.1. And in this video, we're going to take a look at our last example for this series, in that we're going to find the Laplace transform of a piecewise continuous function. So, one of the conditions for Laplace transforms is that they need to be piecewise continuous, and we're going to show like why can be done with a piecewise continuous function that we're able to transform. So we have a piecewise function, f of t equals 0 for the t values of 0 and between 0 and 3, and 2 for the t values greater than 3. All right, and we want to Laplace transform this function. So, remember the definition of Laplace transform. Laplace of a function equals the integral of 0 to infinity e to the negative st times the function we're trying to transform, dt. And so this is a little different because it's a piecewise function, but what we essentially do is split this up into the respective components of the piecewise function. So our first Laplace transform, our first integral, would be dealing with the function 0 that has specific bounds 0 to 3. So our Laplace transform would be 0 to 3 e to the negative st times the specific function, which is 0, dt. Okay, so this is like my function f of t. We're still going from 0 to infinity, but we're broken it down into our specific pieces. And for this function 0, it only goes up to 3. So that's our first Laplace. And then our second transform would be from 3 to now infinity, because if it's greater or equal to 3, and e to the negative st, and our function there is 2. So this is also f of t, just on different range of values for t. Okay, so let's look at this first integral. So e to the negative st times 0. So that's just going to be the integral of 0 to 3 times 0 dt. But the integral of 0 is just going to be 0. All right, we don't get anything from that. Um, that is necessary for us. We could get a constant essentially, but we don't really want to deal with constants with a Laplace transform. Okay, so we could get a constant, but what we can say is just it goes to 0. All right, we don't want like a plus c for our Laplace transform. It's unnecessary going through the transform. So we don't have to worry about that integral. We just have this integral here. Uh, how do we solve it? Maybe we could take out the 2. Okay, and then here it's just like a mental use of that we've seen quite a bit. And so this would be, 2e to the negative st over negative s, going from 3 to infinity. Like we've done with a lot of these, we're going to move this down into the denominator to work out our exponentials that go to infinity or 3. So this was like 2 over s e to the negative st. Gonna move the negative out in front. We're going from 3 to infinity. Excuse me, this isn't a negative right here, just e to the st. And we go ahead and plug in our bounds now. So this is like negative 2 over s e to the s times infinity minus negative 2 over s e to the s times 3. All right, so um, you know, if s stays positive, then this term goes to infinity, okay? Plus 2 over s e to the 3s. You say that. So if s stays positive, that would just be e to the infinity, which means that, you know, this goes to infinity. So I'll have negative 2 over infinity plus 2 over s e to the 3s. And so 2 over infinity, well, that just goes to 0. So I have 2 over s e to the 3s. We could, the way these Laplace looks, they bring the exponent up. So maybe I could bring up e to the 3s. And so the answer could be 2 e to the negative 3s all over s. And that's our Laplace transform. Okay, so therefore, f of s equals 2 e to the negative 3s all over s for s greater than 0. Okay, so that's an example of a piecewise Laplace transform, right? You just got to break it down into the respective functions and their respective bounds. It all works out because it's continuous and it's still going from 0 to infinity. So that's it for this video. Thank you for watching, and I will see you in the next section. All right, take care.